So after having understood the basics of crystal field theory of coordination compound, now in this class we shall explore its one of the most significant application in order to explain the color of the coordination compounds. Now we are already aware that a large number of transition metal complexes, their solution they have a very peculiar color, very specific color, and this property of color was not understood in terms of valence bond theory, and that is where we explored the idea of crystal field theory. So for example, this particular complex compound, it gives the violet color. So with the help of this theory, we shall be looking at later that how this particular complex compound actually exhibit a certain electronic transition in the d orbital, and that absorbs 535 nanometer wavelength, which is yellow color. Okay, so it absorbs yellow color, and when it absorbs yellow color from the white light, then the remaining of all the wavelength together give an impression of violet color. So this violet color basically is the complementary color to the color that has been absorbed by this complex compound. So if we understand the absorption of a certain wavelength by the coordination compound, we shall be able to explain the color of the complex compound. So this color of the complex compound is basically the complementary color. We have already understood this idea of complementary color in our elementary physics classes. But just to have a quick review, what I'm trying to say is this. For example, suppose there is a sample here, and suppose it is imparted with white light, and the white light, even if we consider that it is composed of, let's say, various colors, okay, let's say 7 colors. So there are specific wavelength that are that have gone in the formation of white light. For example, let's say if I specifically call them from lambda 1 to lambda 2 to lambda 3 up to lambda 7, for example, just to limit our the discussion. And then suppose if this sample absorbs a particular wavelength, for example, if it absorbs lambda 1, then if I observe the output light from the other side of the sample, then I will have all the wavelength except the lambda 1. Okay, but I will be actually seeing the impression of mixed impression of all the remaining wavelength. That means I shall be seeing the impression which is caused by the mixture of all the wavelength from lambda 2 to lambda 7, and this is what is called as the complementary color. This is what will be seen as a particular color for this particular sample. So what is absorbed after that, what is remaining, that is being observed is the color of the complex compound or the sample in the water. Okay, so here, for example, in this table, if you look at the first complex compound, it absorbs somewhere at 535 nanometer, which is yellow, and here is complementary wheel. So if it absorbs yellow color, then the color that will be seen as an output of the complex compound will be violet. So complementary color wheel is a quick mechanism to quickly establish or to figure out if a certain color is absorbed, then what color will be seen from that particular sample. So yellow color absorbed, the color of the sample will be violet. Okay, likewise you can explain the color of the observed color or the complementary color of various complexes, because they absorb a certain specific wavelength. Okay, so this particular thing we shall understand. Let's take the example of this particular complex, which is titanium hexaaqua complex. Now titanium hexaaqua complex, in this complex compound, titanium has electronic configuration. Basically titanium has an oxidation number of 3+, and its electronic configuration in the form of d electronic configuration will be d1. Basically you have argon core and 3d1. So there is only one electron in the d orbital of titanium 3+. But then when we consider the same titanium 3+ in this complex compound, then we already have known that this electronic configuration shall be written as T2G1 Eg0. This is according to CFT. Okay, according to crystal field theory. This shall be the electronic configuration of one electron in this complex compound. Okay, this is the octahedral complex. So we are applying crystal field theory to octahedral complex to write down this electronic configuration. What it simply means is that the d orbital in the form of two sets, T2G and Eg, they are separated by a crystal field splitting energy delta O. And the single electron now is in the ground state. Ground state means lower energy state. So it is in the T2G group. But then when I shine white light on this complex compound solution, then this electron, depending upon how much is this particular separation, it will absorb a certain frequency or wavelength. Okay, so a photon which corresponds to a frequency of let's say nu1. Okay, a photon which corresponds to a frequency nu1, and that matches to this energy separation delta O, will be absorbed by this electron, and this electron will go into the higher energy state. That means Eg. So Eg here is a higher energy state and T2G is a lower energy state. So initially electron in the ground state, after absorbing a certain wavelength, in this particular case you can see here the titanium hexa aqua complex absorbed at 498 nanometer. So the wavelength that is being absorbed here by the electron in the ground state of this titanium is corresponding to the correspond to 498 nanometer, and this takes the electron to the higher energy state. Now what has happened is, when we are shining the white light, the remaining wavelength which are not absorbed, they together then give us an impression of the mixture of them give us an impression of violet color. So that means this complex compound in the solution gives the violet color. So it has absorbed a wavelength which is 498 nanometer, which falls in the blue-green region, and the complementary color that is observed is violet. So in this way, our understanding of the formation of a color of a particular complex is based on the electronic transition happening between T2G to Eg type of d orbital, or in general it is also referred to as dd electronic transition. So one can actually establish the relationship between the crystal field splitting energy delta O and the wavelength of light that is absorbed by the electron in order to transit from T2G to Eg orbitals, and that can be very easily given by this relation delta O is equal to h nu1, where nu1 is the frequency of the photon that is being absorbed by the electron, and that can be then translated into the wavelength factor. So here h is the Planck constant, c is the velocity of light, and lambda 1 is the wavelength that is absorbed by this particular electron. And in this particular complex compound, we find that the wavelength of absorption is 498 nanometer, and we just saw that when this particular complex compound absorbs 498 nanometer wavelength, which is in the blue-green region, the output color or the complementary color of the complex compound in the solution that we observe is violet. Now one can investigate this idea of crystal field splitting and hence the electronic transition happening and hence the color of the complex by doing a very simple experiment. So let's say if we take titanium hexa aqua complex and then heat it. So by heating, we are basically destroying the inner coordination sphere, and then this complex compound will now reduce to a very simple compound of titanium 3+, which will be no more a complex compound. So there will be no ligand sphere or no ligand field in this case. And we actually see the consequence of this, that what we observe upon heating is that that the color of the complex, which used to be violet, is now gone, and the simple complex compound is colorless. So how do we understand this? Well, we just saw the color of the complex compound was primarily because of the d-d electronic transition between the two set of d orbitals, the T2g and Eg. All right. So basically the d orbitals were not degenerate in the complex compound. When we talked about the state of the 5d orbitals here, 5d orbitals, they were not degenerate. That means they were split into two groups and having the crystal field splitting between them. But when we heat, since the ligand field is gone, the 5d orbitals have again acquired their original degenerate state. And since all the 5d orbitals are only in one electronic state, now this electron does not absorb in the visible range, and therefore this dd electronic transition is not possible. So this is how we are able to explain that it is the idea of crystal field splitting of the 5d orbitals in the ligand field that helps us to understand the color of the complex compound. One can also take a very common example which all of us have done even in our primary laboratory experiment. When we heat copper sulfate 5H2O, which is actually a complex compound, when we heat it, and the blue color of this is gone upon heating, so we get here copper sulfate. So this complex compound now reduces to a simple compound, and which is white in color. So now let's explore a little further onto the influence of ligand onto the color of the complexes. So why this should happen? How ligand will influence the color of the complexes? Please recall that we have already discussed the different ligand, they can be arranged depending upon what level of crystal field splitting they cause between the two set of d orbitals in a complex compound into the two types. That means weak field ligand, which cause lower level of crystal field splitting, versus the strong field ligand, which cause a little bit higher level of crystal field splitting. And in this example, suppose if we systematically displace in this nickel aqua complex the weak field ligand with the strong field ligand like ethylene diamine. Now remember that ethylene diamine is a didentate ligand, so it can actually replace two of the monodentate ligand like water. And here we see here, so when we do the first displacement, that means we replace two water molecules with one ethylene diamine, we get this complex compound here, and the color of this complex compound is now pale blue. From this, if we replace two more water molecules by one more ethylene diamine, we get this complex compound, and we have the color of the complex compound changing from pale blue now to darker blue. And from this complex compound, if we further replace two more water molecules with one more ethylene diamine, we get this violet colored complex where you have only the strong field ligand ethylene diamine, which is also a didentate ligand. So you just require 3 ligands to form 6 coordinate bond with the metal here, which is nickel. So this is also octahedral complex, this is also an octahedral complex. Now remember, these are the colors which are seen from the aqueous solution of these complex compounds. That means we can actually understand the formation of these colors if we can explain the wavelength of the color that is absorbed by these complex compound solution. And that will require, again, going back to the crystal field splitting energy level diagram of the two set of orbitals from the of the d type. So if we look at this solution, which is solution of nickel hexa aqua complex, and the nickel has an electronic configuration of d8 in this complex, And so is true also in this complex, because both nickel, ethylene diamine and water, they are neutral ligand. So the oxidation number of nickel is 2 plus, and therefore it will have 8 electrons in the d orbitals. Now all we need to do is the distribution of these 8 electrons into the lower T2G and EG orbital, which will be same now in the case of this complex compound and this complex compound. The only difference that we will have here right now will be the level of splitting or the level of energy separation between the T2G and EG type of orbitals. In case of weak field ligand, we will have a lower level of splitting, but in case of strong field ligand like ethylene diamine, in this complex compound, we will have a higher level of splitting. So what will happen is, if we just compare these level of splitting qualitatively, at least, if right now we don't have exact numbers, but let's say if we systematically simply compare the relative magnitude between the delta O and delta O prime, then we see that delta O is less than delta O prime. And since we know that delta O, the wavelength of light that is absorbed is inversely proportional to delta O, because we know this delta O is equal to hc upon lambda absorbed. So the wavelength of absorption of light by the complex compound is inversely proportional to delta O, and therefore we will have a higher wavelength absorbed by the solution of this complex compound, and relatively lower wavelength absorbed by the solution of this complex compound. And in fact, the wavelength that is absorbed by the solution of this complex compound is somewhere in the red region, and the wavelength of the color of the light that is absorbed by the solution of this complex compound, and that corresponds to higher level of splitting, is actually a lower wavelength, which is in the yellow green region. And since this is the wavelength that is absorbed, what we will see as a color is the complementary color. This can be predicted from the complementary wheel. So, if you look at the red color, the complementary color to it appears to be green. So somewhere here, if you see the red color being absorbed here, this red color, the complementary color is somewhere around green. And that is what will be seen as the color of the complex compound solution. Similarly, if you look at yellow-green region, then somewhere here in this range, okay, somewhere here in this range, then the color of the complex compound, its aqueous solution will be somewhere here. That means we see it as a violet color. So we see that the wavelength of absorption here, that has changed from red to yellow green, because the solution of this complex compound absorbs here in the red region, and the solution of this complex compound absorbs in the yellow green region. And what was the cause? The cause is only the replacement of systematic replacement of weak field ligand like water to the strong field ligand by the strong field ligand like ethylene diamine. So what we are seeing here is a kind of blue shift in the wavelength of absorption by the solution of the complex compound systematically when we are replacing the weak field ligand with the strong field ligand. Okay, and the similar effect is also seen into the color which is displayed by the solution of these complex compounds, and which is basically the complementary color. Similar effect is also seen that they also make a shift from blue from higher wavelength to lower wavelength when the ligands are replaced, weak field ligands are replaced by the strong field ligand. So here I have shown you just now that basically the wavelength of absorption is changing from red to yellow green region, and therefore the complementary color of the substance is also changing from green to violet. So basically this is the direction which is same for both the wavelength absorbed and the complementary color that is displayed by the complex compound. So in this manner, this theory actually successfully helps us, the crystal field theory actually successfully helps us to understand the nature of the ligand and their influences on the color of the complex compound also.